Welcome back. In the last lecture, we have seen that if we are considering f is in Schwarz space and considered the heat equation on r cross 0 infinity and u of x 0 is equal to f of x on r, then u of x t, which is equal to f convolution of the heat kernel h t of x, where h t of x is equal to 1 by square root of 4 pi t e to the power minus x square by 4 t. This is going to be a solution, This is what we had observed, and also we have observed that u x t converges to f uniformly as t goes to 0, as well as we have seen that not only this, in the square mean also u x t converges to f of x. Okay. So, now what we are asking about that whether this is going to be unique or not. So, as you can see that if f is in Schwarz space and h t also we have taken it to be in the Schwarz space. So, for each fixed t u of x t is in Schwarz space. For each t greater than 0, u of x t, this belongs to the Schwarz space of R in the space variable. So, what we will observe that this is actually in certain sense this is uniform over t. So, what do I mean by that? So, let us write it as a proposition. U of x or dot t, this belongs to Schwarz space and for each t bigger than 0, supremum over x belongs to R and 0 is less than t less than capital T, mod of x to the power k and mod of del L by del x L u of x t. This is finite. That means, this in some sense this is a uniform over t for all k L belongs to n. Okay. So, first we will show for one u, and for the derivatives the proof is exactly the same. So, now look at mod of u of x t. This is lesser equal to integral minus infinity to infinity mod of f of x minus of y, and then this is h t is a non-positive function. So, this is dy. So, now I break this y integral into two parts. Mod of y is lesser equal to mod of x by 2 and integral of mod of y is greater than mod x by 2. So, now first let us look at this is I 1 plus I 2. Now, for I 1 we know that f is in Schwarz space, thus mod of f of x minus of y is lesser equal to some constant which depends on n and 1 plus mod of x minus y to the power n. Now, where is our y? Y is lesser equal to x. So, look at that x minus of y is greater or equal to mod x minus mod y, and mod y is lesser equal to mod x by 2. Therefore, this is greater or equal to mod x by 2. So, here we can get some other constant d n 1 plus mod of x to the power n. This is for every n, because of the rapid decay of f, what we are going to get this. Okay. So, therefore, if I hit with a polynomial on x, so this is under control. Now, for the second part, so for 2, we have mod of y is greater than mod x by 2. Now, you look at h t of y. This is equal to e to the power minus y square by 4 t. Now, this is I have missed out a factor of 4 pi t 1 half. This is lesser equal to 1 by 4 pi t square root and e to the power minus mod x square by 16 t. E to the power, as you can see that as t goes to 0, this function goes to 0 much more rapidly than square root of t. Therefore, this is a bounded function. So, hence what we have got, hence u of x t is lesser equal to some, for any n, some c n 1 plus mod x to the power n and plus some constant c by square root of t e to the power minus some constant x square by t. Now, this is, of course, if I am hitting with a polynomial with x, and then this will be bounded over the uniform over t. Hence, similar calculation for derivatives of u on the space variable will give us the result. Okay, that is a small observation what we have seen. Okay. So, now let us get back to the uniqueness. So, now for the uniqueness, so what we are dealing with? We are dealing with a equation which is this is our equation. Suppose there exist two solutions for star, that is u1 and u2. So, take V is equal to u1 minus of u2. So, therefore, V t is equal to u1 t minus u2 of t, which is equal to u1 of x x minus u2 of x x, which is equal to v of x x, and v of x 0, which is equal to u1 of x 0 minus u2 of x 0, which is equal to f x minus f x. This is equal to 0. So, essentially if u1 and u2 are the solution of the two equation, and then v is a solution of this equation. So, this essentially says that if we can prove that v t equal to v x x, v of x 0 is equal to 0 on the boundary on r cross 0 infinity on r, then v identically equal to 0 is the only solution. If we can prove this, then we are able to show the uniqueness of the heat equation. So, that is what we will now going to prove. This is theorem. Suppose, and throughout we are assuming that f is in the Schwarz space. Suppose u satisfies the following: 1, u continuous on R 2 plus, u t is equal to u x x, t greater than 0, and u of x comma 0 is equal to 0. Thirdly, u dot t belongs to Schwarz space, uniform on t, because that is what we have seen, that f convolution of h t, that is uniform on t, then u is identically equal to 0. That means, that is convolving with the heat kernel with this condition, when f is in the Schwarz space, then what we are going to get, that it is in fact unique. And the proof is very cute, and this technique is very powerful, used in PDE. So, how to prove this? We want to show that u of x t is equal to 0, and so if we show that E of t, which I will define integral minus infinity to infinity mod of u of x t square d t. Then if E t is equal to 0, then for every x, so then what you are going to get, that u of x t is equal to 0. This is E t is dx. If E t is equal to 0 for every t, then what we are going to get, u x t is equal to 0. If E t is equal to 0 for every t, then u of x t, this is equal to 0 for all x belongs to R, and for all t belongs to 0 infinity. So, that is what we want. Now, how to show that E t is equal to 0? Okay. So, what we first observed is that actually E of 0 is nothing but minus infinity to infinity mod of u of x 0 square dx. This u of x 0 is equal to 0 is given to us. Therefore, this is equal to 0. Now, of course, E is a map from 0 infinity to r positive. This is let us say 0 infinity. Now, u of 0 is 0. Now, if we can show that E is a decreasing function on t, therefore, E of t is going to be 0. So, claim E is a decreasing function. So, how does one show that a function on t is a decreasing function? That means, I need to calculate E prime of t. If we can show that E prime of t is less or equal to 0, then E is going to be a decreasing function. So, let us try to calculate what is E prime of t. So, this is d by dt E of t. So, this is equal to integral minus infinity to infinity. We can put the integral inside mod of u of x t square, then this is dx. Now, this is minus infinity to infinity del by del t of mod of u x t into u x comma t bar dx. So, this is going to be minus infinity to infinity del by del t of u x t into u bar x t plus u of x t into del by del t of u bar of x t. This is dx. Now, what we know? We know our equation as u t is equal to u x x. So, we will replace this minus infinity to infinity. This is u x x, this part, and then this is u bar plus u. Now, obviously, if u t is equal to u x x, then u bar of t is equal to u x x bar. Therefore, this is u into u x x bar, this of dx. Now, in the first integral, what we do is that this is minus infinity to infinity u x x u bar plus minus infinity to infinity u of u x x bar. So, by applying integration by parts, so what we get? This is u x u bar minus infinity to infinity minus integral minus infinity to infinity u x, and then the derivative is u x bar, plus in the second term also this is u into u x bar, this is minus infinity to infinity, then minus of integral u x and then u x bar, this is dx. Now, remember that u is a Schwarz class function, Therefore, u x is also in the Schwarz class function. So, both u and u x, they are going to vanish at plus infinity and minus infinity. So, here what we have got, this is minus infinity to infinity mod of u x square dx. Now, this is a non-negative quantity and heated with negative this. So, this is 0. Hence, E is decreasing. Therefore, E t, which is equal to lesser equal to E of 0, which is equal to 0. And we know that E t is always greater or equal to 0, because we have defined it to be the integral minus infinity to infinity mod of u x t whole square dx. So, this will imply that E t is equal to 0, that is and u is a continuous function. So, this will imply that u of x t is equal to 0, that is uniformly over t. So, now this is u is identically equal to 0, that is what we wanted. So, what we are saying is that if f is the initial value problem, if f is the boundary function and u satisfies the heat equation and the condition we are imposing f is in the Schwarz space, then certainly what we are getting is that this is the solution is unique. Okay. So, now we will apply the similar kind of technique now for some other PDE. So, let us take our attention to the PDE of the form. Consider on this is again we are looking on R 2 plus, which is equal to, here I will make a little change of the notation, x is in R and y is greater than 0. This is the upper half plane. Okay. Consider delta of u, which is defined to be u x x plus u y y. So, now if we are looking at this is equal to 0 on, and u of x comma 0, this is equal to f of x. This is the equation we are considering. So, there u x x was equal to u y, that is the heat equation, and this is the Laplacian equation what we are considering in the upper half plane. Okay. So, again we play the game of Fourier transform by taking the Fourier transform on the x variable on both the side. What we are going to get is that by taking this is u x x hat at xi comma y plus this is going to again change, this is what u y y hat at xi comma y, this is equal to 0. This implies that this is minus 2 pi I xi square and u hat of xi y plus, Here, as we have seen, the time uh, uh, variable differential operator commute with the Fourier transform on the space side. So, here we will get del square by del y square of u hat at xi y. Again, by defining our phi of y to be u hat xi y for each fixed xi, this will translate it to minus 4 pi square xi square phi of y plus phi double prime of y, which is equal to, this is equal to 0. Now, this is a second order ODE, and with the condition given that phi of 0, this is nothing but f hat of 0. Now, this second order ODE is going to have a solution for each fixed xi. This is a xi, what we know that e to the power minus 2 pi mod xi y plus some b constant depends on xi, because for we are playing this game for each fixed xi 2 pi mod xi y. Remember that y is positive and the kind of solution we are looking for is a bounded solution, and this is no more a bounded, not bounded. So, therefore, we can ignore this. So, this is, we can take b xi to be 0, this is phi of a xi e to the power minus 2 pi mod xi y. We know exactly that phi of 0 is equal to f hat of phi of 0 is f hat of xi. Therefore, this a xi, this is going to be equal to, by this condition what we get is that this is equal to f hat of xi e to the power minus 2 pi mod xi y. And now, this if p of y, if I am defining to be a function such that for each fixed y is minus 2 pi mod xi y, then this is f convolution of p y hat at xi. Again, what we get is that the solution, it is going to be then u of x t, this is equal to f convolution of p y x y is equal to f convolution of p y of x. Now, what we need to find what this p y is, it looks quite familiar to us when we have dealt with the Poisson kernel as a good kernel in the series case. And in the next lecture, we are going to see what is the form of this Poisson of this p y such that p y hat of xi is e to the power minus 2 pi mod xi by y mod xi y. Thank you.